All right, here we are, the last lecture. We've made it, right? No, I'm sure the time has flown by. So here we are finishing up Chapter 10 on acids and bases, finishing up Chem 141, the course, and hopefully working together again for Chem 142. So please, consider that if that's a course you need, and we've worked well together here. I hope we can work together again. So this very last section of Chapter 10 on acids and bases deals with buffers, and buffers are a very important part of biological systems, chemical systems, and we'll explore them in greater detail here, but first we'll have to define and understand buffers, and it is a topic that, although important, is sometimes difficult to get your mind around at first, so please don't get frustrated. We'll make sure that you get there. So a buffer solution maintains pH by neutralizing added acid or base. So if you add a little bit of acid or a little bit of base to a buffer solution, even if it's strong acid or strong base, typically if it's fairly small amount and you have a good buffer, it will resist any pH change, or maybe very moderate or minor pH change compared with what would happen in pure water, for instance. If we think about biological systems in the body, we can absorb H3O plus or OH minus from foods and cellular processes to maintain pH. We get very different pHs for different parts of the body. The gut has a very low pH because the hydrochloric acid in the gastric juices. If you go into the small intestine, now you have a relatively high pH, and it's important that those areas have their pHs in those ranges. Blood itself, which contains buffers to maintain a pH pretty close to 7.4, is a pretty critical pH. If you get a change in blood pH either higher or lower by any measurable amount, you can disrupt oxygen absorption, you can disrupt metabolic processes. If it gets really high or really low, you can precipitate proteins and have enzymes stop functioning. So it's very important, especially in biological systems, that we can maintain a very stable pH. So here's a little visual to help you understand just how important buffers are and just how significant their function can be. So if we have, in the top case, just plain old water, if we add a little bit of acid or base to the water, well, if we add some acid, we have the pH drop drastically from 7.0 to 4.0, so that's 3 orders of magnitude greater H3O plus concentration. If we do a similar thing with the OH minus, we can have that drastically go up from 7.0 to 10.5, so over 3 orders of magnitude there for whichever concentration of base we added. If we do the same thing to a buffer solution, now we have a very, very, very minor pH change. So if we add some acid, the buffer might start at 7.0 and go down to 6.9. So very minor increase in H3O plus concentration and a very small decrease in the pH. If we did the same sort of thing with some base, again, whereas in the unbuffered water, it caused a drastic 3.5 orders of magnitude increase, for plain water, in the buffer we just go from 7.0 to 7.1. So these buffers are very, very good at resisting pH change. They do tend to decrease in pH when you add acid and increase in pH when you add base, but much less so than an unbuffered solution would. So now just how buffers are able to do that amazing work is based on how the buffers are made up. So the components of a buffer solution, if you think back to our Bronsted-Lowry definition of acids and bases and conjugate acids and conjugate bases, a buffer solution is an acid-base conjugate pair that have nearly equal concentration. So you can have a weak acid and the salt of its conjugate base, you can have a weak base and the salt of its conjugate acid, but you've got to have the conjugate of whatever weak acid or weak base you start with. Again, it's weak acids and weak bases because strong acids and strong bases don't make buffers, they make salts. So they ionize completely and you get a salt when you have a strong acid and a strong base. But when you have a weak acid and a weak base, you have the ability to have the acid form react with additional OH minus to convert it to its conjugate base. You have the ability for the base form to react with added H3O plus to form its conjugate acid. So that's why it's important that you have the acid and its conjugate base, or the base and its conjugate acid, because then you resist pH change by having conversion from one form to the other, whereas in pure water, you just get the H0 plus and the OH minus allowed to cause drastic changes in pH buffered solutions, you're mostly converting between forms and relatively little change in H0 plus or OH minus concentration will occur. All right, so let's see how well you understood that last point about the components of a buffer. So in this learning check, you're asked, will each of the following combinations produce a buffer solution or not? Explain. So you have A, B, C, D. Go ahead and assess whether or not you think they would form a buffer solution. Remember, you're looking for an acid and its conjugate base or a base and its conjugate acid. And if you don't have that, then you would not expect it to be a buffer. If you do have that, then you would. So go ahead and pause the video here, make your determinations, start back up once you've figured it all out. All right, so in the first case, A, you have HCl, which is a strong acid, and KCl, which is a neutral salt. So in that case, we're not going to expect an acid base conjugate pairing to form a buffer. Instead, what we're going to end up with is a strong acid and a neutral salt that's going to give rise to just a very drastic pH decrease upon addition to water. If we look at B, now we have a weak acid, carbonic acid, H2CO3, and we have sodium hydrogen carbonate. So the hydrogen carbonate ion is the conjugate base of the weak acid, carbonic acid. So this is a weak acid, and its conjugate base, the sodium ion, doesn't really matter. It could just as well be potassium or lithium or whatever. But because we have the weak acid, carbonic acid and its conjugate base, in this case sodium salt of hydrogen carbonate, we would expect buffer behavior. If we move on to C, now we have a weak acid, H3PO4, but we have a neutral salt. It's not the conjugate base. We'd need some sort of hydrogen phosphate or dihydrogen phosphate in this case, and we don't have that. We just have another salt, a neutral salt in the form of NaCl. Finally, for D, we have a weak acid, acetic acid, and we have potassium acetate. So again, it didn't matter if it was potassium or sodium or lithium, but having the acetate ion, which is the conjugate base of the acid that we have here, acetic acid, we would expect a buffer behavior. So B and D would act as buffers because we have a weak acid and its conjugate base. A and C would not act as buffers. A because the KCl, HCl is a strong acid, so Cl minus is not a base to any appreciable extent. And then finally C, we have the weak acid, but we don't have its conjugate base. We have NaCl instead. So if you didn't get those, if you're still struggling, please do try some additional practice problems and certainly reach out to me. We didn't do anything together first, so I was sort of throwing that out there. Hopefully you got it. If not, we're going to talk more about buffer action here, and hopefully that will help clarify any issue you might have had. Okay, so far we've said we need a weak acid and its conjugate base, or a weak base and its conjugate acid, but we haven't exactly explained why that will allow for buffer activity. So here we take the weak acid, acetic acid, which was one of our acids from the learning check, and then we have, in this case, sodium acetate as opposed to potassium acetate from the learning check. Doesn't matter, the counter ions are irrelevant. It's really the acetate ion that we care about here. So if we think about the weak acid dissociation, the acetic acid acting like a weak acid, we would have the acetic acid plus water forming the acetate ion plus proton, H3O plus in this case. So that's an equilibrium process. It's a reversible reaction, and actually it doesn't go very far to the forward. It goes mostly in the reverse direction. It mostly stays as neutral acetic acid molecules dissolved in water. If we think about the conjugate base, the salt here, we get another source of the acetate ion, right? Instead of just relying on the little bit of acetate that we form from the acetic acid, now we're putting a soluble sodium salt of the acetate ion, so we can get a lot of acetate ion present. We can get essentially equal concentrations of acetic acid because it stays mostly as acetic acid, and then acetate ion because we can put the soluble sodium acetate in solution. So if you look at that reversible reaction up top, if we look at the reverse reaction, the acetate ion can take on H3O plus to reform acetic acid in water. That would be a way to soak up H3O plus to resist the change by adding a strong acid to a buffer solution, by consuming that H3O plus according to Le Chatelier's principle and forcing the reverse reaction. Likewise, if we added a strong base, well, we'll have to wait till the next slide for that. I don't want to get ahead of myself. All right, so sticking with the same example, here we have now the weak acid, acetic acid, can neutralize added base. So if we look at the acetic acid itself with water from the previous slide, it doesn't go very far to the right. But when you have a base, a source of OH minus, now you can force the reaction to go essentially to completion. Until you use up the free base, the OH minus ions, you're going to go in the forward direction. And so therefore, we can take our acetic acid, and when we add the OH minus, we get the acetate ion formed and water. So you can see that we don't really have much free H3O plus or OH minus in these cases. We just have a relatively different amount. If we started with equal amounts of acetic acid and acetate ion on the left, we see as we add OH minus, we end up with a little less of the weak acid form, a little more of the conjugate base form, and very, very little OH minus increase. Again, there's a slight amount. As we saw, the pH might go from 7.0 to 7.01 if we add base, but not like adding the base to pure water. Now, if you weren't following me a couple slides ago when I talked about the acetate ion being able to neutralize added H0+, we can see here that acetate ion, because it's the conjugate base of a weak acid, can act like a base, can soak up that H0+ to form neutral acetic acid and water, and so we get the reverse process happening here. Now, if we look at the right, we have relatively equal amounts of weak acid and conjugate base forms, and as we add H0+, we have slightly more weak acid form, slightly less conjugate base form, and very little extra free H0+. So again, if we added this to pure water, we might go down by 3 pH units. If we add this same amount of acid to the buffer solution, we might go down by 0.01 pH units. So it's a drastic change, and it's because of that ability to transfer between weak acid and conjugate base form, or weak base and conjugate acid form in a buffer system. Instead of the H0+ going all to lower pH, or the OH minus all to raise pH, it's just changing the relative amounts of weak acids or weak bases present. Okay, so in summary, the buffer action occurs because the weak acid in a buffer can neutralize any added base, the conjugate base in the buffer can neutralize any added acid, and the pH of the solution is maintained to the majority of the extent of pH. Again, you might get small decreases in pH with the addition of H0+, like 0.01 units, or small increases in pH with the increase of OH minus, like 0.01 units, as opposed to 3.0 or 3.5 as we saw with pure water. So if we look in the center, we always like to start our buffers with roughly equal concentrations of weak acid and conjugate base, or weak base and conjugate acid. As we look to the right, that would show us adding OH minus, which means we're going to deprotonate some of that weak acid form and end up generating more of the conjugate base. If, on the other hand, we went to the left and added H0+, we're going to cause the conjugate base to take on some of that H+, and therefore increase in amount and have the acid form, weak acid form, increase as a result, and then have less conjugate base because some has gone on to react with that H3O+ ion. So hopefully you got the concept down. That's the most important part, right? Of course, in this course, we also like to do calculations. So now that we have a basic understanding how buffers act, let's talk about calculating the pH of a buffer system. So the H3O+ concentration in the Ka expression is used to determine the pH of a buffer. So we remember weak acid plus water is in equilibrium with H3O+ and the conjugate base. So the Ka, if we talk about the acid dissociation constant, is going to be the H3O+ concentration times the conjugate base concentration divided by the weak acid concentration. If we rearrange that to solve for H0+, we would get H0+ concentration equal to Ka times the inverse of what we saw before. So now weak acid in the numerator, conjugate base in the denominator, and ultimately pH, if you recall, is equal to minus log of H0+. So if we can find the H0+, then we can take the negative log of it to find the pH of our buffer system. You're used to this by now, I'm sure. It's our guide to calculating pH of a buffer. So now that we have a calculation, we're going to have our, in this case, 4-step guide to performing that calculation. And first and foremost, it involves writing the Ka expression. Then we rearrange that Ka just as we did in the previous slide to solve for H0 plus concentration. We substitute the HA concentration and A minus concentration at equilibrium into that Ka expression. And then finally, once we've solved for that H0 plus concentration, we can substitute the H0 plus into the pH equation, pH equals minus log of H0 plus, to calculate the actual pH of the buffer. All right, so let's see how that works. Let's actually calculate a buffer pH. So the weak acid dihydrogen phosphate in a blood buffer, H2PO4, the dihydrogen phosphate, and the hydrogen phosphate, monohydrogen phosphate, has a Ka of 6.2 times 10 to the minus 8. What is the pH of the buffer if the concentration of H2PO4 minus equals 0.20 molar and the concentration of HPO4 2 minus equals 0.20 molar? Remember, we said that buffers tend to work best when we have equal concentrations of acid form and base form. So step number one, we'll analyze our problem. We see that we're given the acid molarity and the base, the conjugate base molarity. They're both 0.20 molar. We have the Ka of the weak acid, and we know that we need to find the pH. We have the equilibrium acid-base chemistry reaction there, H2PO4 minus plus H2O in equilibrium with HPO4 2 minus plus H3O plus. Okay, so step one, we can write the Ka expression, and so Ka in this case from that weak acid dissociation would equal HPO4 2 minus concentration divided by times H3O plus concentration divided by H2PO4 minus concentration. So we can rearrange this to solve for Ka. To solve the equation rather for H3O plus concentration. The Ka is the most important feature. This is why you have different buffers made of different acid-base pairings for different buffer ranges. So you can have a pH 4 buffer, that's usually an acetate and acetic acid buffer. If you want something around pH 7, you want this buffer that we're looking at here with the dihydrogen phosphate, hydrogen phosphate buffer. And that's because they each have a unique Ka, and the Ka gives you the range around which your buffer is active. So that's going to determine what sort of buffer system you want is the Ka, more so than anything else here. Okay, so rearrange that Ka to solve for H0 plus as our second step. In our third step, we can substitute in the Ka and the HA and A minus concentrations. In this case, because they're the same, they give us 1, right? 0.20 molar divided by 0.20 molar equals 1. So really our H3O plus concentration is equal to our Ka. That's why I said the Ka is pretty critical for determining the pH at which a buffer system works, because ordinarily your acid and base form are pretty much the same, so it's the Ka that determines that range. And then finally, the pH would be minus log of the Ka, also known as the pKa, and that would be 7.21. So that's how we know this buffer would work well around pH 7.2, which is where, again, we said the blood is around 7.2 to 7.4. All right, so let's see how well you followed all that with this learning check. So in this learning check, you're asked what is the pH of a carbonic acid buffer that is 0.20 molar carbonic acid and 0.10 molar hydrogen carbonate ion. So be careful. Here they're not the same, and you won't just get the negative log of the Ka. You will have to do a little more than that. So be careful. And the Ka for a carbonic acid is 4.3 times 10 to the minus 7. So go ahead. It looks like it's going to be in the range of 6 point something. So all the answer choices seem to be around there. So go ahead, work through our guide, and hopefully you'll come up with the correct answer. Stop the video here, do that work. Once you've made your answer choice, start us back up to see how you did. Okay, let's see how you did here. First, we'll analyze the problem, which is I hope what you did, just like we did in our sample problem that we worked together. We see here we're given the acid molarity 0.20 molar. The base, the conjugate base, is 0.10 molar, so just be careful. They were different here. The pH is what we're looking for, and the Ka in this case is 4.3 times 10 to the minus 7. The equation for carbonic acid acting as a weak acid is carbonic acid plus water in equilibrium with the hydrogen carbonate ion plus the hydronium ion. Okay, so according to our guide, step 1 is to write the Ka expression. So looking at our balanced chemical equation, we see that the Ka is equal to the hydrogen carbonate ion concentration times the H0 plus ion concentration divided by the H2CO3 concentration. Again, we don't put pure liquids like water into an equilibrium constant expression, so that's why it doesn't appear. Step 2, we can rearrange that equation to solve for H0 plus, and then we get H0 plus equals Ka times H2CO3 divided by HCO3 minus concentration. Okay, moving on to step 3, we can substitute the value for Ka, the value for the HA concentration, the value for the A minus concentration into our equation, and we end up with an overall value of 2.2 times 10 to the minus 7. So it doesn't change a whole lot from the 4.3 times 10 to the minus 7, which is the value of the Ka itself. So as I said, that's the most important feature, and then the relative amounts of acid and base form can cause you to move a little bit, but you're basically going to be right around that pH value that's closest to the pKa, the negative log of the Ka itself. So in this case, it wasn't the same because of the concentration of acid and base form being different, but we see in step 4 we can use the H3O plus that we calculated up there, and we find our pH is equal to minus log of 2.2 times 10 to the minus 7, and that gives us a value of 6.66. If we had just taken the minus log of the Ka, 4.3 times 10 to the minus 7, we would have gotten 6.37. So we can go up and down a little bit, usually plus or minus 1 pH unit from the Ka, the pKa technically, the minus log of the Ka is where a buffer will act well. So let's see how well you understand that concept here with buffer preparation. A buffer solution is needed to maintain a pH of 3.5 to 3.8 in a urine sample. Which of the following buffers would you use if 0.1 molar solutions of the weak acid and conjugate base are available? So if we look at the formic acid and formate ion conjugate acid base pair, that Ka is 1.8 times 10 to the minus 4. If we look at the carbonic acid bicarbonate buffer system, that Ka is 4.3 times 10 to the minus 7. And if the ammonia buffer system is considered, and that's the first time we've looked at a neutral base and then its conjugate acid, that Ka would be 5.6 times 10 to the minus 10. So because we'd have equal molar concentrations of acid and base form, just like our first sample problem together, that part of the equation would cancel out. So really we're just looking for the pKa, the negative log of the Ka for each of these, because that's what we're assuming the H0 plus concentration would equal, and so we'll see how well we do with figuring that out. All right, so if you look at the values there, actually, to get a rough estimate of the pH where things would be good buffers, we can just look at the exponent of the Ka as long as we're assuming equal concentration of acid and base form. So our rough estimate for the pH of a formic acid formate buffer with equal concentrations of formic acid and formate ion would be around pH 4. If you do the math, it's 3.74, and again, buffers tend to act well around 1 pH unit around their pKa. So from about 2.74 to 4.74 is where we might expect formic acid to be a reliable buffer, and really it's in that middle area that it works best. For carbonic acid bicarbonate, again, because it's times 10 to the minus 7 for the Ka, we'd expect it to work well around pH 7. Actually, if you do the math rigorously, you find it's a pH of 6.37, so anywhere from 5.37 to 7.37 is where it would act as a reasonable buffer. And then finally, for the ammonium-ammonia buffer, that's going to be around pH 10. If you do it rigorously, it's actually pH of 9.25, and so it would be expected to have some buffer activity between 8.25 and 10.25, but it's going to act best right around that 9.25, the negative log of the Ka. So in this case, because we were looking for a urine buffer, we would want something with a pH close to 4, and therefore the formic acid formate buffer would be the best choice. The one other thing I do want to mention about buffers is the idea of buffer capacity, and so it would be remiss of me to leave this without saying that if you have lots of strong acid or lots of strong base and relatively small concentrations of weak acid and conjugate base forms for the buffers, it's not going to work forever. If you sat there and drank a bottle of Drano, don't ever do that. It's not a good idea because it's a strong base. And yes, you've got buffers in your body, but they have a capacity. You can't just take on infinite amounts of strong acid or strong base. A little bit your body can resist, but again, a little bit is a few drops, not a gallon of Drano or a gallon of muriatic acid. We have to be very careful because buffers do lose their ability to act as you get more of one form predominating, and then finally you've converted all of the acid or base to its conjugate, and it's not going to act like a buffer anymore. All right, so there we have it. The last thing I wanted to say about buffers, the last advice I have to give you here in the course as far as lecture goes. Hopefully you've enjoyed the course. I've enjoyed having you along, and please do consider joining me for Chem 142 if you need the second half, where we'll talk a lot about the organic and biological chemistry, whereas this semester was devoted to the general chemistry. All right, so good luck. Hope the course ends well for you, and hope to see you again soon.